Good evening, everyone. I hope you can hear me. I'm Cecilia Restelli, and I'm the chair of the Scientific Organizing Committee of Enable. Sorry, I had some issues with my audio. Actually, I was saying that I'm Cecilia Restelli. I'm the chair of the Scientific Organizing Committee of Enable 2021, and I'm a fourth-year PhD student at the European School of Molecular Medicine in Milan. And I'm really pleased this evening to welcome you to our cross-disciplinary session that is titled "The Trophy Would Not Fit the Suitcase Because It Was Too Small: Machine Learning Between Science and Narrative." In this case, I would like to underline the fact that in the past, during the Enable Symposia, we used to organize the cross-disciplinary session as an activity mainly for the general public. But this year, we decided to integrate it in the scientific program of the event. And so it's available for both the Enable participants and also the general public that are now seeing this event on YouTube. In addition, this year, this event was organized together with Extemporanea, that is a group of, let's say, a community of scientists and that are both university students and researchers located all around Italy and Europe. And the main activity of Extemporanea is the Science Ground, that is a series of events of science communication that are organized during the big Festival Letteratura of Mantova. And but now I think it's time to present our speakers to shed light on the cryptic title of tonight's event. So it's my great pleasure, first of all, to introduce you Professor Harry Collins, that is a distinguished professor of social science at Cardiff University in Wales, UK, and among the several honors and awards that he received during his career, it's worth to mention that he was elected Fellow of the British Academy in 2012. In addition, he has written for over 30 years on the sociology of gravitational wave physics, and in particular, I would like to mention one of his last book that came out in 2018, that is Artificial Intelligence Against Humanity's Surrender to Computers. So thank you very much, Professor Collins, for being here tonight with us discussing on machine learning. Actually, it's also my pleasure to present you our second speaker, that is Dr. Matteo Polettini. He obtained his PhD in theoretical physics at the Alma Mater Studiorum University of Bologna and is now research assistant at the University of Luxemburg and is working on non-equilibrium statistical mechanics. So welcome to you too, Matteo. Actually, right now we're gonna start with a presentation from Matteo that is gonna start explaining us a little bit the concept of machine learning, and then we will start a little bit of discussion, just letting also Harry Collins to intervene. So welcome everybody, and Matteo, the stage is yours.
Thank you. Thank you to the organizers. I hope that the audio is fine. Please give me feedback because I did not have a clue. Is it okay? Yes.
Yeah, I can hear you.
Okay. So I'm very happy to be part of this enterprise by Enable. I'm not an expert. I'm an expert actually in non-equilibrium thermodynamics, which is very much in line with the title of the Enable initiative, which is taking place, which is exploring life dynamics in and out of equilibrium. But today, instead, I will discuss a little bit something I'm not expert on. So this is it's a brutal challenge. I can share my screen. and this thing is machine learning. And I want to discuss machine learning as a non-expert because I'm very curious about it from both a social point of view and a scientific point of view. So I'm trying to guide myself through it. And as I do it, I think it's nice to share what I'm understanding about it. So now I'm sharing my screen. Can you please confirm that you see this white slide handwritten? You can?
Yes. Yes, I can.
Yes. Okay, so we're going to discuss about machine learning and how I personally understand it. So machine learning is a very broad concept. It's a set of algorithms. They have been around for quite some time. Actually, there have been several springs and winters of machine learning. And recently, it's on the verge of popularity. It's a conflated concept together with other words like artificial intelligence, which is something related but not identical to machine learning, and which I actually don't understand. But let's talk about machine learning. So the point is a set of algorithms that try to solve very well-defined problems. So for example, a very well-defined problem is to decide whether the image of a cat is a cat or the image of a dog is a dog. And another well-defined problem is to, given the initial state of a check match between two opponents, to decide what is the best next move, okay? So these are two very different problems, and the solution that is being given in recent times to these problems falls under this wide hat of machine learning algorithms. But as we will see, maybe it's a very broad concept. So if we try to idealize a little bit what these concepts are, it's actually quite simple in theory. It's not quite simple in practice. But the idea, and here I will use a little bit of math, but not too much, just to try to be precise, is that there is some function which maps some data, x here, to some label, for example. So for example, the data could be the bit of an image. So you can imagine that this is just how the image of a cat or of a dog is coded into bits of information into your computer. And this function maps it into some values, which, for example, could be +1 if the image is a cat and -1 if the image is a dog. And here we would like to have a true function in the sense, in some philosophical sense, which I don't know exactly what it is. But of course, we never have the true thing. We can at least approximate it. And that's what machine learning algorithms are all about. Machine learning algorithms are algorithms, which is functions from a mathematical point of view, that give an approximation of the true function into something which performs well on given data. So, for example, so this A here is my algorithm, is taking data and is taking labels which are already known, because maybe we have used human intelligence to learn how these data behave, and we want it to spit out some function that approximates the behavior of the true function, okay? And this data here, they can be very many. They will be very many in general. So they go from 1 to n, and this n is a very big number. So, and once we have this approximating function, we can use it to generalize. So, for example, we take a new picture. So this x prime here is the data related to a new picture, and we spit out the new label. So, for example, we feed the algorithm, the function that the algorithm estimates by a new picture, for example, this one, and our algorithm will tell us whether it's a cat or a dog. So, okay, there is a lot of, I'm oversimplifying, of course. There's very many machine learning algorithms out there, and it's very difficult to catalog, to establish a catalog of algorithms. More or less, some of the useful concepts to guide through these algorithms are that these algorithms can be supervised or unsupervised, for example. So these two big frames. Supervised means that basically the training sets, the data that the algorithms works on, and the labels are provided by humans or by other algorithms. So in this sense, the algorithm is performing against external information, okay? For example, here is a very nice picture meme by the well-known SKCD, the scientist, very much. So I had information, for example, for self-driving cars, and we also have to be very quick if we don't want the cars to do accidents. Of course, it's not like that, but it's a nice way of seeing it. Unsupervised is training and given by the algorithm are internal to the algorithm itself. The algorithm learns without interface with the human. So, for example, we could take chess. It's well known that AlphaZero, which is the Google powerhouse for chess playing, now wins against Stockfish, which is the best old-style non-machine learning algorithm, deterministic, and it does it in a very spectacular way. And this algorithm, AlphaZero, did not learn to play chess against human data or historical data about chess, but it just plays against itself zillions of games, I don't know the number exactly, and it learns patterns inside the data, okay? But in fact, I must say, this is a little note, is the distinction between supervised and unsupervised is actually a bit more blurred than what I just said, because it's never, of course, algorithms always interface with humans to some respect. So it's not such a clear-cut distinction between supervised and unsupervised, but it's more on the way of how resources and how the algorithm itself is constructed, okay? Another important distinction is between deterministic algorithms and stochastic. So, well, here is just deterministic algorithms, given the data, they will produce the same, even while stochastic data, which can be produced again by the interaction with humans. Okay, I don't want to be too long on this. I just want to give a little bit of a little hint on how these algorithms even work. So again, we have this function here, a, and now we appended a little theta here, which is a set of internal parameters that the function wants to learn, okay, given the data z. And So this is the most technical part. I hope that all those will stick to this, because later on we will discuss more about the sociological and philosophical aspects of this. But I have to go through a little bit of this for those who are more interested into the technicalities. So the point is that the algorithm is trying to figure out what are the best values of these parameters given the data. And they do so. So we have to assume some functional form for our algorithm, which is the architecture of the software. And then we minimize the error of the data with respect to the true values of the labels. For example, this is one way to do it. There's many ways to do it, okay? So we just perform our algorithm and see how good it does. And then we assume that it does good, and we apply it to more data that come later, okay? I will not go through these considerations, but just one point I want to make is this is nothing new. In principle, it looks like it's nothing new. We have been doing this in physics, in mathematics, in all of the sciences forever. We have been fitting functions. And from what I told you so far, there is no difference between fitting a function and a machine learning algorithm. It would look like. So what's actually new? Let's go into this. Suppose we have our data x1, x2, which are just points with y being some label here. And let's assume that there is a true function f that, from which these data are drawn. And there can be errors, okay? Sometimes the data just don't come out quite as the theory should give. If we were fitting usually using Taylor expansion, for example, we could start from a linear fit, okay? Then we would parameters, phi0 and theta1, and we would fit this data with a straight line. And well, does it work well? Maybe yes, maybe no. We have to discuss this. We can go on. We can add more fitting parameters. Now we have 3 parameters. We are fitting our data with a quadratic curve. And does it do good? Well, it's better, right? It looks more similar to the true function. But we could go even further. We could say we have 6 parameters, 1, 2, 7. And now with this many information, we can fit all of the data. The curve that we chose is so precise that it can fit all of the data. But the problem is it will not be able to generalize well. See, this is the true curve. We've taken some new data which are out of the set. And the true curve says it should be here, but our model, which we trained too much, is over here. And this is a well-known problem in machine learning and more in general in statistical inference, which is called the bias versus variance conflict, and which is closely related to another known effect in data analysis, which is the curse of dimensionality. If we have too many parameters to measure something, then there is no average behavior, the statistics, so anything fits. Okay. But, and now I come to my final point for this technical part, but it seems that neural networks do not do that. It seems they are powerful enough to go beyond this problem of overfitting. And this is a bit of a mystery. So I will not go into the details of what a neural network is. I think most of you will have seen this sort of picture. There is some input data, there is some output data, and in between there are neurons, and each neuron processes the information from coming from previous neurons, and it just does it through a linear function. But then it put through some very non-linear function, which is something that imitates the idea of making a decision between two choices. For example, the logistic function imitates what it means to be a dog or a cat with some precision, let's say, okay? And finally, you cook it up into this big thing, which I'm not going to explain, but basically the idea is just you take the data and possibly the labels, you make transformation, you throw them into the logistic function, you feed them back, you make transformation, you feed them into the logistic function, etc., etc., etc. And the point is that this thing is highly nonlinear and is nowhere close to the way we represented functions, for example, by Taylor expansion or by Fourier analysis. Okay? So this nonlinear character of the transformation, that on the one side there's curse of dimensionality anymore. It seems like it's not there. It seems that these machine learning algorithms, the more parameters they have, the better they do, which is contrary to intuition about what fitting a curve is. But also on the other side, we don't have control on what these functions have, because all these non-linearities make it so that we cannot reconstruct back what the parameters are and how the parameters behave in response to data. So this is a very fancy image I stole from someone else's talk about. This is the reconstruction of what machine learning algorithms, a neural network, sees as relevant pattern in image recognition. And it's nowhere close to anything intuitive. And we just don't have theory to explain why this pattern is particularly relevant to this algorithm. So all these considerations have repercussions on what it means to validate a scientific discovery by means of machine learning, given that we don't have theory and control of what the algorithms do. And furthermore, there also exists a more sociological problem, if you want, which is the file drawer problem. And this is basically that there are so many data. One could argue that the reason why we have machine learning all over today is that there's more data to analyze, right? And this huge mass of data, of course, is interesting for many reasons, and of course there are also reasons of politics and power behind that, and in corporate interests. From a scientific point of view, as a scientist, I point out that there are an enormous abundance of data can create the so-called file drawer problem, which is a problem that Harry Collins, who we'll talk later, has very well analyzed in his book Gravity's Ghost, where he analyzed the practices of the gravitational community. And basically the file drawer problem is very well explained by this beautiful cartoon by KCD again, which is, if we can generate hypotheses by the number, like correlation between the form and shape and color of peas and I don't know what's the effect here, and having acne. And if we do enough experiments and we do not declare all of the experiments, then there is a high percentage of probability that one of these experiments will turn out true. Okay? So we find correlation between green jelly beans and acne. But just because we did not declare openly that we performed another 19 experiments in between. So this is one, as a scientist, one of the critical points I see with employing machine learning within science to do data analysis is that not only we do not have complete control of the theory, but the data are so abundant and the means of analysis of the data are so abundant that we could just easily generate fake correlations. And this is something that defies the usual rationale of scientific inquiry. Finally, machine learning and artificial intelligence require to rethink what expertise is, because it's not about physicists anymore, it's not about computer scientists anymore or engineers anymore, because there is a very close interplay between the architecture of the algorithm itself, and how the data are collected. And so we have to sort of rethink what expertise in these areas is. I just give some references. These come from a very physicist-oriented perspective. And I let Collins have a few words now.
So thank you very much, Matteo, for your contribution. And based on your intervention, I would just like to ask Professor Collin a question that will allow him to start speaking about his field. And actually, I was wondering, what are the differences between the gravitational wave community that you studied so long and the artificial intelligence community?
Okay, thanks for asking me that question. You can see me now at the moment, but you cannot see my PowerPoint. I'll put it up in a moment. Let me just say something about who I am. As you said, I'm a sociologist of science, or sociologist of scientific knowledge. So I spent 45 years with the community of gravitational wave physicists, from the moment that it was near the moment that it was originally suggested that gravitational waves had been seen, to the moment that they'd agreed, that was in the very early 1970s, to the moment that they'd agreed that gravitational waves had been seen in 2016. And I followed the whole thing through and tried to work out how science was done by watching these physicists. Now, the other thing I was doing at the same time was thinking and writing about artificial intelligence, because I thought it all started off with my very early studies of the nature of how the way scientific knowledge is made, suggested to me that some of the claims that were being made around 1990 about the nature of artificial intelligence were just wrong, because that's not how human knowledge is made. And I've now written 3 books about artificial intelligence and how it compares with how human knowledge is made. So the overall question I'm asking, and have been asking for a very long time, is how is artificial intelligence working as a science which should explain how human intelligence works? So one of the things science is for, a science of human beings anyway, is to tell you how human beings work. And artificial intelligence has told us a lot about human beings' work. For example, it's told us that the really difficult things to automate in human intelligence are not the things that you used to be thought of as being very, very, very clever when I was at school, say the ability to do mathematics in your head, mental arithmetic as it was called, because any little pocket calculator can do that. The really difficult things are fluent speaking of a native language, because we still can't get computers to do that. Not really well. That's why this overall session has that title. Can you just repeat that title, Cecilia?
Is the trophy would not fit the suitcase because it was too small.
Right. Now, the question is, what is it that was too small? Was it the trophy or was it the suitcase? And you have to know that before you can do a bit of machine translation from English into French, because the French nouns are gendered. And if you don't know whether it's the trophy or the suitcase that's too small, you'll get the gender wrong when you do the translation. And certainly 2 or 3 years ago, the best machine learning algorithms couldn't translate that sentence properly. A simple sentence like that. And in my book, which I'll show you a picture of the cover in a moment, I've got lots of examples of this sort of very, very simple thing that computers, artificially intelligent computers, can't handle. Very simple things indeed. But you don't hear much about them. What you hear about mostly is the success of intelligent computers. And that's one of the ways in which the science of artificial intelligence differs from the science of physics, as I observed it happening over 45 years in gravitational wave detection. The thing that the gravitational wave physicists were most scared of was announcing that they'd seen a gravitational wave and it turning out to be wrong. But the scientists of artificial intelligence don't seem to be too worried about that. They seem very happy all the time to say, yes, we've finally created artificial intelligence. They do it over and over again. You know, and the standard test of whether a machine is intelligent is the Turing test. Can it produce fluent language? And they keep saying it can. And then other people like me have to say, no, it can't. Here's an example of what something your machine can't do that any human can do. Like know whether it's the trophy or the suitcase that's too small. Easy. Now, let's get to machine learning, which is what Matteo was talking about. Machine learning has been a tremendous success in artificial intelligence, neural nets. It has been enormously successful. And it's far better than any previous artificial intelligence program in mimicking what humans can do. And this actually thrills me. I don't mind. I wish artificial intelligence would be successful tomorrow. I think it would be a very interesting thing. And if it was, I think I'd learn a lot more about the nature of human intelligence. And so I'm delighted with the success of machine learning. And I think machine learning is success. I think I can explain in very general terms why machine learning is as successful as it is. And for that reason, I'm going to put up my slide. So what do I want to do? I know I've just got to click on that, haven't I? And click on that. Now, can you see my slide? Hello?
Yes, they are loading. Yes, now we can see them.
So you should see a blank page with a picture of the cover of my book in the top left-hand corner. Is that right?
Exactly.
Okay. Now, this book is the third of a series of 3 books I've written about artificial intelligence. I hope you like the title, Artifictional Intelligence. And what animated this book and made it hard to write and interesting to write was the fact that machine learning had come along and was being much more successful than previous artificial intelligences. And there's a chapter 7 where I try and explain something about machine learning. And if I press this, there we are. That's Matteo's image of a neural net. And I'm going to assume that everybody roughly knows how that works. It's supposed to be, and the brain is said by, shall we say, somebody like Ray Kurzweil, to be a really complicated neural net. And in other words, a set of hierarchical pattern recognizers. And there's an image from my book, which is somebody called Sam. I chose the name Sam because it's gender neutral. And there's Sam's brain, and that's the neurons in Sam's brain arranged in a series of hierarchical pattern recognizers. The top level takes a look at what comes up from the lower levels. And because the top level has a lot of experience and knows a lot of images like cats and dogs and things like that, it will say whether what's coming up from the bottom levels are reasonable or not. And this is a neural net. Now, why are neural nets so successful? Well, we can see if we take a look at the next slide, because that's not really how a brain works. This is how a brain works. There's Sam's brain in Sam's head, but actually Sam is getting continual feedback from all the other brains in the society in which Sam is embedded. So the number of neurons is not limited to what's in your head. The number of neurons is far larger than this. It's enormously larger than this because it includes all the neurons in all the heads of other people. Think about it. That's how you learn language. You learn language by being brought up in a family. And in that family, you're being fed examples of good language use by your parents initially, and then by all the other people in society. And of course, your parents have learned it from all the other people in society. So your learning of language is being continually modified and monitored by the whole of society. And as you know, language changes as society evolves. There are sorts of words that your teenage children, if you have teenage children, say that you probably can't understand, but they can understand because language is changing. Now, neural nets are so successful in handling language because neural nets can embed themselves in the language spoken by society. They do it by embedding themselves, by reading what's on the internet, or by embedding themselves in huge examples of language or something like that. But the reason they're not as successful as humans at speaking language is because they're not embedded in all those other neural nets that you see are monitoring social SAM. Now, I think the neural net idea is a good one. It seems to me to be quite reasonable that the brain is a hierarchical system of pattern recognizers. But if you're going to make it become as fluent as a human speaker, you're going to have to allow it access to the entire language of society, the entire language of speakers, in just the same way as a young child is brought up. And at the moment, we have no idea how to do that. And that's why it's hard to translate a sentence like, it's hard to know whether it's the trophy or the suitcase, which is too small, because to know that, you've got to have a whole lifetime of experience. So I'll stop there for the moment, and I believe Matteo had some, and maybe others have some questions. So shall I stop? I'll stop screen sharing now, shall I?
Yes.
Right. Didn't stop.
So actually, if Matteo doesn't want to add anything else, I would like to ask something else. Because based on your really inspiring presentation, based on like the concept of machine learning and artificial intelligence and how they kind of are interdisciplinary, should we reconsider disciplinary boundaries? And if yes, as a scientist, how can we actually practical intervene to obtain these results?
Sorry, so can you just say your question again? You want to know whether the science of artificial intelligence we should it should become interdisciplinary? Did you say?
Yeah, exactly. How can we reconsider?
Which disciplines?
Yeah.
Which disciplines? Do you
think because since you were discussing we can consider machine learning and artificial intelligence from a mathematical or physics point of view, but since we need the information that came from the society or also from, let's say, how social beings and humans interact among themselves, it's clear that if we consider those machine learning and artificial intelligence per se without kind of putting together the knowledge coming from different fields, becomes difficult to have, let's say, a complete visual and to obtain something that it's kind of really mirroring what we are as human beings. Is this right?
Well, the interdisciplinarity that I think you need is an interdisciplinarity between artificial intelligence people, the technical people, and people who've got some idea about how humans learn. So people like me. But in fact, I'm kind of doing interdisciplinarity. I'm trying to do interdisciplinarity by writing my books about artificial intelligence. I'm already saying, look, guys, if you want to make a successful artificial intelligence, you better take notice of what I'm saying. Now, whether people will actually take any notice of it or not, I don't know. But this is the thing that disappoints me, is that the artificial intelligence community don't seem to have set themselves up to discover the difficulties in what they're trying to do. They seem to have set themselves up to persuade everybody else that they've already succeeded. And this is most unlike physics. So let's take a field of physics like high energy physics. In high energy physics, it's very difficult to get good criticism of what you've discovered, because all the really good critics are already in the field of high energy physics. And so you're getting you're asking your friends to criticize you. So what people do is quite formally, they set up what are called red teams and blue teams to argue against each other in order to get good criticism. Now, I don't see anything similar like that happening in artificial intelligence. What happens in artificial intelligence is something like this. We say it's very hard for a machine to translate that sentence about trophies and suitcases. Somebody works out a way of translating the sentence, and then they say, there you are, it's been done. And then we go on and say, but well, all right, how about this sentence? And then they say, every time we find a solution, you find another problem. Well, of course we do. That's what you're supposed to do as a critic. The real trouble is that it's the artificial intelligence community who should be finding those extra problems, one after another, until they've really cracked the problem. But they seem reluctant to do it. So that's the kind of change I would have said is needed. But as for what an artificial intelligence needs to learn to translate a sentence like that in a natural way, well, I think every parent already knows it. If you ask a parent, would you like your child trained by being exposed to a huge database of examples of written language, or would you prefer to bring it up in a continual human interaction with you? I think most parents would say, hey, if they just are exposed to a whole load of examples of written language in the way that machine learning artificial intelligences are, they won't wind up as a proper human being. No, they need to be immersed in a household and all the other experiences that humans are immersed in if they're going to turn out to be to mimic human intelligence and human abilities.
Yeah, thank you a lot for this contribution, and I would like to hear also the opinion of Matteo on this topic. So if you please can.
Yes, on the topic of the difficulty of the challenge that machine learning community faces, I have a little slide here. I will just show you these curves. These are generated by, I'm teaching myself a little machine learning algorithm just to get the idea of what it is all about and why we should do it and what are the difficulties. So, I can tell the full story. I will not go through all of this, but basically, I am part of a group of young researchers and PhDs and postdocs who try to have a more nuanced and complex conversation on social aspects of science and science. And since a few years, we run some laboratories, some workshops with children of all ages on machine learning. And we just took inspiration by this very nice MANES. It's Matchbox Educable Noughts and Crosses engine. It's a well-known mechanical algorithm that learns to play match and boxes, which is just not you put this thing. We do it with another game, not this one, but it's called NIM, and you can just basically two players alternate and they cross some bars, and the guy who crosses the last wins. Okay, so this is just a very simple two-player game, and we are training a mechanical algorithm. This is our algorithm, this is our apparatus, to learn by many learning rules. For example, we have the pruning rule, the trimming rule, the reinforcement rule. I will not go through all of these things. We can give a pretty complete mathematical description of the game. Also, it happens that the space of moves of the game is a beautiful fractal. This just came out of our simulations, and when we saw it, we were like, wow, that's nice. And interestingly, so this is the very crucial point, this NIM plus game is solved, meaning that there is a complete theory behind it. And so we know the truth. We come back to this idea. I know this word should not be used so easily, but we have something to compare with, okay, which most machine learning algorithms do not. So it's a different framework, and then we program this algorithm which self-reinforces the learning. And so this is, for example, a scheme of how it learns the good moves, the green ones, the bad moves, the red ones. Yellow moves are those that are not yet learned, and the gray moves are those that are not good and it doesn't learn. And the point, finally, I'm back to this figure, is that because we can compare to theory, we can see, so this is the very important point, there is a learning curve of the good moves. The algorithm is learning the good stuff. That is okay. But while it is learning the good moves, it is also learning a lot of bad moves. And then a long time is spent to unlearn these bad moves, to take away this information. And interestingly, the algorithm, this red curve, you can only obtain because you can compare to theory. There's nothing like this for chess. There is nothing like this for language, or it's just because the model we chose is so stupid and so simple that we have a complete full theory to compare with. Otherwise, we would not be able to actually observe this curve. But something like that could be there. So now, finally, I'm up to my question to Harry, which is actually a question that I took from a friend of mine, Christian, who's a sociologist, who has worked for a long time on expertise. And he realized that ignorance is an important ingredient in establishing expertise. So when an expert establishes what is important to know, he also establishes what is to be ignored. Okay, and there is even a field of discussion which is called agnotology about ignorance studies. So finally, I ask Harry how ignorance plays a role in his own theory of expertise and studies of expertise. And finally, I also promote a little bit the work that we do as Extemporanea. We are based at Festival Letteratura, which takes place in Mantova. Harry has been there a few years ago to discuss about the gravitational wave and some of our links and sites. And yeah, the workshops I just illustrated. We have tried to give them with school children, but of course now we are stuck in the situation that we all know. So finally, back to Harry on how ignorance enters his own system of thought.
Well, I have a lot of my own ignorance. Perhaps that's not what you're asking. I don't know this study, Agna. I've heard of it, but I haven't made a close study of it. Of course, science can't proceed without ignorance, because one of the ways you have that one of the things that's involved in making a scientific discovery. Let us think about the discovery of the first gravitational wave. One of the things you've got to do, if you want to say this is a discovery, is stop criticizing at certain points. So, for instance, the discovery of the gravitational wave involves readouts of various instruments. And you've got to stop asking, but are you sure you know how those instruments worked? You know, the voltmeters. Are you sure you trusted the person who published the paper? There are lots of questions that you have to stop asking if you want to have some stable body of knowledge. I don't know if that touches on your question, but that's the best answer I can give.
Yeah, thank you a lot. If I mean, we are almost finished, but since we received some questions for the audience, I would like to forward you one that seems really interesting. Enrico Massignani is saying that he recently learned that there are artificial intelligence which are being trained to cooperate. So is this a good way to somehow reproduce social interaction? And if you can comment on it, please.
No, it's not a good way. I don't even know what it means. If you think about it, ants and bees cooperate all the time. That's how they have their hives and their nests. But you wouldn't say they had human-like social intelligence. They don't. They have information exchange. It's got nothing to do with the way humans understand things.
Okay, thank you a lot. And there was also another question regarding the criticism that can be moved to machine learning and artificial intelligence that is coming from Sara Del Cenjo. And do you think they has to come from the community itself or from some external agents?
Well, it would be better if it came from the community itself, simply because the community itself contains the real experts and they're the best experts at criticizing. They really know what's going on. So at the moment, it has to come from outside, from people like me, and I have to scrape around to find out what's going on. And I don't really keep up with the technical frontiers of the discipline. I kind of did when I was in the gravitational wave field, but I spent 45 years traveling around the world, going to all their conferences, spending a lot of money and having a huge carbon footprint. Now, it would be better, if the experts were doing the criticism and saying one of the things that we should have as a kind of rule of our subject is that nobody will say that the Turing test has been passed by an intelligent machine until it's passed all this set of 100 tests, some of which you can find in my book and other of which you can find from one or two interesting critics of AI from more within the field.
And Matteo, do you want to say something regarding these?
No.
You just agree?
Yes, it's perfect, yes.
Perfect. So lastly, I would like to hear your opinion about regarding another question that was asked actually. How far do you think we would be able to push the machine learning and the AI in the next future? And how far actually we should push them before starting putting some kind of boundaries or limits?
Yeah, I don't know is the answer to that. Again, in my book, there's a table which sets out 6 levels of artificial intelligence. And I think at the moment, we are struggling to move from level 2 to level 3 in my table. And I don't think that the levels that you have to worry about the dangers that supposedly computers will take us over and keep us as pets, they don't occur till levels 5 and 6. And that's a long, long, long way off. That doesn't mean to say that computers aren't dangerous. Computers can kill us quite easily without being intelligent at all. You don't have to, they are killing us actually because of all the hackers and various other people breaking into them and making them not work properly and breaking down our power systems and our banking systems and things like that. So computers are quite dangerous enough as it is without being intelligent. And quite honestly, I think the big fuss that we had a few years ago about computers taking us over, it was misplaced. That won't happen. It's not something we need to worry about for a very, very long time. It's not a matter of intelligence. It's of artificial intelligence. That's not the danger.
Thank you a lot. And Matteo, do you want to add something else, or you just agree with Professor Collins?
Well, with this last, it would take another 2 or 3 hours to go into this. But I think there is one aspect of artificial intelligence which is not dangerous in itself in the way that algorithms are being used on top of society, but on the way that data are being produced to feed these algorithms, which is already affecting society in deep ways. So I showed you before the triangle. So it's not just the algorithm and it's not just the structure of the theory or the data, but they are all come together. But the moment when you pose, for example, the problem of how a car can self-drive on the streets, you are also imposing at the same time a political statement on what streets should be and on how they should be driven and on how they should be built to be monitored, to be driven by cars that will eventually self-drive in a distant future. So now I'm speaking not as a scientist anymore, but more of a informed person who has issues with conceptual issues with machine learning being deployed in society, which is more about not so much about the algorithm taking over, which is it's very far probably in the future, but it's more that it's taking the preparation of the ground for the algorithm to take over is already affecting how society is built.
It is, but it's not to do with their intelligence. It's to do with their lack of intelligence. That's the problem.
Yeah.
Because if the self-driving cars could drive like human beings, we wouldn't need to change anything.
Yeah, actually, I don't know, Matteo, if you want to say something else, or Professor Collins.
Only thank you for listening to me. And if anybody wants to send me a question, then it's easy to find my email. Yeah,
definitely. Actually, also this is going to be available both on YouTube and from tomorrow also on the platform of the event. So thank you very much, because it was really inspiring. And actually, we explored, let's say, parts of machine learning and artificial intelligence that maybe were not really clear, especially for, let's say, the scientific counterpart. And so thank you very much, Professor Collins, and thank you a lot, Matteo, too. And thank you to all our participants and the public also on YouTube. Thank you a lot.